was a time when the ring of the anvil was a familiar sound in every town and village. But that was a long time ago. So long, in fact, that some might think the blacksmith's craft is one of the lost arts and belongs to the days of our grandfathers. Actually, this is far from true. Although the art of forging is as old as history itself, its practices have been transformed to fit our modern needs. Today's forge is a modern oil or gas-burning furnace where billets of special quality steel are brought to forging heat. The blacksmith's hammer has grown to a powerful machine that multiplies the strength of his muscles 1,000-fold. His crude anvil now appears as a carefully made die that shapes the hot metal with swift precision. Thus, the skill of the smith, as important now as it ever was, has been aided and abetted by many other skills, so that now we can forge the metal faster, reproduce the desired contours exactly, and as many times as may be needed. A fundamental fact about forging is the quality improvement that hot working imparts to the metal. This is a natural consequence of the forging process itself, which allows the original grain flow of the metal to conform to the contours of the finished piece. It works in our favor equally well whether the forging blow is struck by the hand hammer of the blacksmith or a 1,000-pound board drop hammer or a 50,000-pound steam-driven giant. But huge forgings like this are the exception, not the rule. To learn what forgings really mean to us in our daily lives, let's take an example we all know about. For instance, the family car. It's a convenience we all take for granted and one we'd have a tough time getting along without. It takes a lot of forgings to build a car. Normally, of course, they're concealed beneath a handsome exterior. But if we just dissolve that exterior away, leaving only the vital chassis, then we can take a really good look at its works. Let's start with the engine, whose component parts are made of many materials and by many processes. Cylinder block and manifolds are cast iron. In the distributor, we find a shaft that is machined to size and shape from solid bar stock. Fan blades are stamped from sheet steel, and so are cylinder head covers. Valve rocker arms are steel forgings, and so are many of the vital parts that transmit the engine's power. Connecting rods, crankshaft, and transmission gears, universal yokes and crosses, and differential gears and pinions. And in the chassis, the steering knuckle, arm, and kingpins are all forgings. Our car is thus a beautifully integrated whole, built up from many kinds of parts, each suited to its particular kind of service. Where maximum strength and toughness are essential, these parts are forgings, because forging develops the utmost quality in the metal through refining and controlling its grain structure. A connecting rod is a first-class example of this. Here is the die in which the rod is made. Its two matching halves contain the impressions that correspond to the shape of the rod. In use, the dies are mounted in a drop forging hammer, the lower half fixed, while the upper half is fastened to the ram, which can fall freely to bring the two matching halves together. The connecting rod starts as a steel blank of the proper size, called in the trade a multiple, which is heated in the furnace until the steel becomes somewhat plastic and will flow under the blows of the hammer. Here's what the rod looks like after trimming and cleaning. This one has been cut in two and the exposed surface polished, then etched with acid. This reveals how the grain structure conforms to the shape of the piece, concentrating the grain density and fiber formation at the points of greatest stress. Most forgings are made in drop hammers. One widely used type is the board drop hammer. It gets its name from the hard maple boards that are attached to the ram. At the top of the frame, they pass between, but do not quite touch, continuously running rollers. Whenever the ram has fallen to deliver, the rollers automatically press against the boards and drive them upward, carrying the ram up to its top position. Then the boards are caught and held by wedge action until the hammerman releases them for the next blow. This cycle will repeat itself automatically as long as the treadle is held down. This hammer is rated at 2,500 pounds, that being the weight of the ram. Board hammers run up to about 7,500 pounds and make forgings up to about 30 pounds. Another kind of gravity drop hammer is the airlift hammer. Instead of boards to raise the ram, an air cylinder and piston do the work. Operating the treadle lets the ram fall freely of its own weight. An important feature of the airlift is that the hammerman can control the length of stroke, varying the blow from light to heavy. This is a steam drop hammer. They are usually built bigger and heavier than gravity hammers, run in falling weight up to 50,000 pounds, and use a double-acting steam cylinder to raise the ram and to drive it downward so that the force of the blow is greatly increased. The ram is automatically kept moving up and down between working strokes in order to prevent condensation of steam in the cylinder and valves. By varying the steam pressure, the hammerman can deliver a light or heavy blow as required. Steel multiple usually has some surface scale as a result of heating, and this is removed by an air jet or steam nozzle. Steam hammers using closed dies produce drop forgings weighing up to several tons. You have probably noticed how the hammerman uses different cavities in the die as the work progresses. The most important reason for this is that full development of proper grain flow in the metal requires progressive forging steps. To show how this works out, here's a typical die. Its two halves laid out so we can study these steps. And here we have a number of partly finished forgings to show what each step does. This is the fullering impression and is the first one used. Holding the multiple in this position reduces the section of the metal for the shank of the rod. The edging impression is next. It is used to gather the stock where it will be needed for the larger sections, such as the big boss on the crank end. In blocking, the next step, several blows form the hot metal into approximately its final shape. The final operation is done in the finishing impression. Now all details of the final shape appear, the maximum improvement in the quality of the metal has been achieved, and the piece is ready for trimming. Here is a set of trimmer dies consisting of the die and the punch. When set up in a press, it will shear the flash off cleanly, leaving a finished forging of the exact shape required, needing only a bare minimum of machining before assembly. Some forgings are made in another type of equipment called a forging machine or upsetter, of which this is an example. In upset forging, the hot metal is worked not by hammer blows, but by applying squeeze pressure to the heated portion of a bar of stock, displacing the metal and forcing it to fill a cavity in the die. The die itself is made in two halves, which open to admit the stock and close to grip it tightly on each work stroke of the machine. The finished forging appears on the end of the bar of stock and needs only to be cut off, a job usually done with speed and accuracy by a fast-cutting hot saw. Looking down into the machine from above, we can see that the actual displacing of the metal is done by a ram or header that moves into the die cavity on each work stroke. These wooden models show how the header operates, moving into the cavity from the rear of the machine. This is called a three-pass die, with 3 cavities and 3 headers, corresponding to 3 progressive stages in forming the metal to its final shape. The first 2 headers are hollow. Removing a portion of one will let us see just how it works. The blank is merely a bar of forging steel heated to working temperature. It is inserted in the die cavity, which then closes around it, gripping the bar tightly at this point. Now let's look inside the die and see what happens when the heading tool is brought into position. Pressing on the end of the bar with great force, it shortens and expands it to fill the hollow in the header, then withdraws. Now the piece is transferred to the second cavity and the ram moves in again. This further shortens and expands the piece. Now it is ready for the finishing cavity or the final pass. This time the header, a solid bar, expands the stock to the full diameter of the finishing cavity. When it withdraws, the completed forging may be removed from the die. To make larger or more complex parts, dies with more cavities and headers are used. This one, with 4 passes, produced this forged blank for a gear shift countershaft. This gear cluster forging was made in a similar set of dies. Cutting it at 2 and etching with acid shows the control of grain structure and fiber formation achieved by upset forging, which results in a finished part of maximum strength and durability. Another means of forging by the use of squeeze pressure is the mechanical press. Presses like this are capable of exerting up to several thousand tons of pressure on the hot metal. This press is making shell casing bases. The simple round shape is very well adapted to high-speed press production. Only 1 die cavity is needed for this forging, although 2 strokes of the press are required. The first one upsets the metal blank, breaks the scale, and partly positions the grain flow. On the second stroke, the upset blank is forced into the die impression, which gives it its final form and finish. For large forgings of aluminum or magnesium, a hydraulic press is often used. This one is capable of exerting 18,000 tons of pressure, and even larger ones are being built. Here we see aluminum alloy being worked into an impeller wheel for a jet engine. Right now, a billet of the alloy, heated to forging temperature, is being pre-worked between flat dies to improve its grain structure. Next comes the first pressing or blocking that brings the billet roughly to shape. Then, in a second die, the finishing strokes give the forging its final form. As in any other kind of closed die forging, the hot plastic metal is forced to flow step by step into the contours of the finished piece, with its grain structure developed and improved at each step. In addition to hammers and presses, auxiliary forging equipment is often used. For example, forging rolls reduce a short, thick section to a long, thin one, or modify the cross-section of the stock prior to forging. In this case, partly finished forgings are being elongated and tapered to make tractor gear shift levers. Some preparatory forging is done with plain flat dies. The method is called Smith forging and is here being used to make a tongue hold on this billet to prepare it for a closed die hammer. This is a trip hammer or helve hammer, another type of auxiliary equipment. A typical use is drawing out and tapering large stock preparatory to finish forging in a closed die, thus making for a simpler die in the drop hammer. This, like all other auxiliary equipment, is one more means of utilizing closed dies to the best advantage. Because it's the closed die and all the technology that goes with it that combines the benefits of mass production with the fine quality of forged metal. So the die itself is the focal point of the whole process, and the making of the dies a vital part of any forging plant. Die blocks are made from special alloy steel, forged to the dimensions needed for each die to be made, and heat treated to assure maximum hardness and die wear. The first step is to drill holes in each block into which handling bars may be inserted for easy manipulation of the heavy block while in work. A planing operation machines the shanks that will attach the dies to the ram and the anvil of the drop hammer. The next step is to plane two edges of each block at exact right angles to each other. The die maker will use these matched edges as baselines in laying out the die impressions. The face of each die block is dressed in a surface grinder. This will result in a smooth, accurate surface upon which to do the layout work. Now the die maker has begun the layout work, the outlining of the die impression on the face of the block. When this is completed, the impressions are sunk into the die, beginning with the finishing impression that gives the forging its final size and shape. It is located near the center of the die, so the weight of the falling ram will be centered on the forging. While the block is still in the machine, the other impressions are also roughed out, subject to final corrections that may be needed later on. After machining the impressions, there is always some handwork to do: scraping, filing, grinding, and polishing the cavities. When this has been completed, the two halves are clamped together and a proof of the finishing impression made by filling it with molten lead or dye compound. This proof will be carefully checked for accuracy and sent to the customer for approval. If all is well, the other impressions can then be completed and the finishing impression surrounded by a gutter, a shallow depression for receiving the flash or slight excess of metal squeezed out by the finishing blows of the hammer. The completed dies are finally ready for careful inspection to make certain that all dimensions are correct and that finish is up to standards. Equally important, the edging, fullering, and blocking impressions are studied to make sure they are properly shaped to direct the grain structure of the metal to best advantage step by step as the forging progresses. Every forging die needs a corresponding trimmer die, and the work is generally planned so they're both ready at the same time. Since this is to be a hot trimmed job, the die maker is using the same lead cast that was made as a proof of the forging die to check the contour of the trimmer die. When the completed forging dies are finally installed in the hammer and lined up carefully for exact registration of the two halves, then the painstaking work that went into the planning, making, and checking of the dies gives assurance that they'll do their work perfectly from the first forging on. In the normal process of drop forging, the steel receives a certain amount of beneficial hot working, and in some cases may need no subsequent heat treatment. But in most cases, like these gas engine crankshafts, Forgings was specified because the part had to have maximum strength and toughness. Heat treating is needed to develop these qualities to the fullest possible extent. This is a typical modern continuous type heat treating setup. The forgings first enter the hardening furnace, where they can be brought to any specified temperature from 1400 to 1900 degrees Fahrenheit. As they fall from the belt at the end of the furnace, they drop into the quenching bath below. This can be whatever water or oil bath is required to obtain the desired properties. The conveyor takes the hardened forgings up and across to the tempering furnace, where the slow process of drawing is accomplished. This is by no means the only method of heat treating forgings. There are many others, just as there are thousands of kinds of forgings, each needing the special treatment required to suit it for its job. After forging and heat treating, there is still a thin layer of iron oxide or scale on the surface of the steel. This can be removed by mechanical or chemical means. The chemical method is called pickling and consists of dipping the forgings in an appropriate solution long enough to loosen and remove all scale, then rinsing them in neutralizing solutions and water.